Okay, so here we are. So section 1.2. So we're going to start talking about vectors now. And so what is a vector? I'm going to start off by talking about some physical / geometric concepts that you're already aware of, just as kind of a segue in there. So one is, first thing I want to talk about is the idea of a displacement. And so y'all know what a displacement is. You were here and now you're there, right? So a displacement says, I'm going to move in some direction by some distance. So, for example, if you start here and then you end here, right? Well, then you have displaced in that direction by that amount. Right? And notice that what we have here, this process of having done this displacement, there is a direction of the displacement, and there is what I'm going to call a magnitude. There's a distance in this case, but okay. All right. So a direction and a magnitude. Okay. Now here's a different physical concept: velocity. Right? So it's not the same thing as a displacement. A displacement is just, look, I was here, now I'm there, end of story. Right? Velocity talks about the continual movement of time and how your position changes with respect to that time. I mean, this is a very more sophisticated, really, much more sophisticated concept. Nevertheless, if you have a velocity, your velocity is in a certain direction. Right? And there's a what you might call a magnitude of your velocity, namely speed. How fast are you going? Right? Not all movements in this direction are the same. I could be going slowly in that direction. I could be going fast in that direction. Right? So here's what's interesting. The eyebrow raiser here is that even though displacement and velocity are really different notions, as it turns out, they both have associated directions and, different particulars, but that said, they both have associated magnitudes. So this pairing of a direction and a magnitude, we already have two examples where that pairing of a direction and a magnitude is interesting. And there are others. This idea of a direction and a magnitude. Forces, right? I'm holding up my stylus here. Gravity is applying a force to my stylus in a certain direction, that being down, right? The definition of down. And with a certain magnitude, namely how heavy is my stylus. Okay. So it turns out there's actually lots of examples where this pairing, a direction and a magnitude, is really, really natural. It's a sufficiently important pairing that we're going to give it a name, and the name is, we call this pairing a vector. So it's just, very often this is the case. We create mathematical objects because, they keep coming up in applications in a lot of circumstances. Okay. All right. So here's a couple of examples, and these are slightly different. Here I have a vector in what I'm going to call a vector in R2. So notice we're in 2 dimensions. This is the XY plane, 2-dimensional world, and this thing right here is a vector. Because it's got a direction, namely what direction is the arrow pointing, and it has a magnitude, namely how long is that vector. Okay. Excuse me. By the way, arrows are a really convenient way to represent vectors, because a vector, keep in mind, now very importantly, a vector is a combination of a direction and a magnitude. Well, arrows point in directions, and arrows have magnitudes. They're kind of not quite perfect, but they're pretty close to perfect ways to represent vectors. This one's a little different. This is a vector that's in R3. Notice that we are in 3 space, right? And so this is not just a matter of which way are we pointing horizontally, but there's also sort of a vertical aspect to keep in mind as well. Still, direction and a magnitude. Okay. All right. So now let's look at this picture here. How many vectors do you see here? I ask rhetorically, and a lot of students will say 4. And I say no. We have here 1 vector. This is a subtlety. A lot of students get a little too comfortable with this idea of using arrows to represent vectors. And I've got to emphasize that arrows are a tool for representing vectors, but it remains that the vector is just the direction and the magnitude. Arrows have this other awkward feature that I have to draw them with a pencil. And therefore, this is just how pencils and paper work. They have locations too. Vectors don't. Vectors do not have a location. Vectors are a direction and a magnitude. That's it. Right? So the fact that I physically drew that arrow on the page like that, well, I mean, I needed something to represent this ethereal, abstract notion of just a direction and a magnitude, and the way I represent it is with something that has other features that I do not care about. Right? The fact that that arrow is located a certain place on the page is not what I'm trying to describe. The vector is just the direction aspect of that arrow combined with the magnitude aspect of that arrow, and all other characteristics of the arrow are irrelevant. The fact that I have highlighted it in purple, that's not part of the vector. It's not a purple vector, right? And the fact that I've drawn it on that location on the page, also not part of the vector. So if you look back down here, again, now how many vectors do we see here? Well, there's 4 different arrows. But these arrows all point in the same direction. They are all of, forgive my artistic imperfection, of the same magnitude. These are all representing the same single vector. Everybody on board? It's an important distinction to be clear on. Okay. Alrighty. So now there is a big difference. You'll recall we talked about points last time in the 5 minutes that we actually spent doing math last time. We talked about points in RN. What is a point? So a point is a location, right, with coordinates. Right. And now we've just now talked about vectors in RN, and vectors don't have a location. Very importantly, they just kind of float around or something. But vectors have directions. Vectors have magnitudes. Points don't. Points don't have a magnitude. Doesn't make any sense. Right? So these are different things. But that said, even though they are different things, there is a very natural one-to-one correspondence between these. There's a pairing. There's a buddy system. For every point in RN, I can associate in a natural way a unique corresponding vector in RN, and vice versa. All right. So the way that works, it's based on this idea of what we call standard position. Now, this is a quick aside. Standard position for a vector means that I'm representing that vector with an arrow whose tail is at the origin. That's what standard position means. All right. So with that said, here's the nature of the one-to-one correspondence between points and vectors. So let's suppose we're interested in this point. And the question is, in this little perfect pairing, in this buddy system, that point corresponds to what vector? I ask. And here's the answer. The correspondence is going to be, let's just associate it to the vector in standard position whose head is at that point. This is an arbitrary rule. There's nothing magic about this rule, but this is very standard, and so we're going to go with this. Okay, so you give me that point, that green point there, and the associated vector is a vector represented by that arrow, standard position, head at the point in question. And you'll notice there is exactly one arrow that does that. That arrow is one of the representatives of the appropriate vector. Now, don't forget, so is this arrow. This arrow and that arrow, these all represent the same vector. So that's why I like to draw more than one of them here. What I will say is the single vector that is represented by all these purple arrows, that's the vector. One vector that corresponds to this point in green. Okay. All right. How does it go the other way? Well, if you have a vector What's the associated point? Well, if you have a vector, then it's represented by a bunch of arrows, a lot of them, right? But of these many arrows representing that vector, there will be exactly one whose tail is at the origin, right? That exactly one that's in standard position, and that one, its head, is the location of the corresponding point. Okay, so this is like I say, a perfect pairing. It's a buddy system. Everybody's got a buddy, right? You give me a point, there's exactly one corresponding vector, and vice versa. Okay, so with this in mind, because there is this natural one-to-one correspondence, it is actually pretty convenient to take these different things, these different ideas, vectors in Rn, not the same as points in Rn, totally different things, and yet we're going to kind of conflate them. I'm going to use points as a tool for representing vectors, and I'm going to use vectors as a tool for representing points in different situations where it happens to be convenient. And the confusion should never actually be a confusion, because these are in fact different things, right? So if I make reference to a vector, but I refer to it as a point, then okay, what I mean is the point that corresponds to that vector, and vice versa. Okay, so the way this ends up being useful is when it comes, first of all, when it comes to representing vectors. How are we going to represent vectors? We don't want to sit there and draw arrows all the time. I mean, that's highly geometric. What's an algebraic way to represent vectors? Well, I'm going to represent vectors by the coordinates of the associated point. Right? We have this fantastic algebraic way of representing points, ready to go. So I'm going to use those coordinates to represent the corresponding vector. Okay. Likewise, I will very often refer to points by their corresponding vectors. And there's reasons why this is convenient sometimes too. I'll show you an example coming up in a few minutes here. Okay, all right. So again, we're blurring the distinction between these two very different things, and I emphasize they are different. But this sort of sloppiness, deliberate sloppiness of terminology and notation is very convenient. Okay. So for example, let's suppose that this is 1 and this is 3. Then I can refer to that vector as the vector 1, 3. Or I can refer to that point as the point P with an arrow over it, namely representing P as a vector, even if I in fact mean the point. Okay. And context will make it clear which you're actually talking about. Now, just as a cultural note, I want to let you all know that not all books are as comfortable as I am with blurring this distinction. And there's an argument there, right? Fully granted, right? So in some cases, you will see, I don't know if you can see, here, let me zoom in because I don't know if it's visible on this small. Some will use these triangular braces instead of round parentheses as an indication of, look, these numbers 1, 3, what I'm going to do with these numbers 1, 3, triangular braces mean I want to think of those two numbers as coordinates of a vector. That triangular braces are the indication that I don't mean the point with coordinates 1, 3. I mean the vector whose associated point has coordinates 1, 3. All right. So I'm not going to be doing that in this book or this course, but you'll see that around, and that's all that means. It's not a big deal. Okay. Another thing, heads up. It ends up being really convenient sometimes to take coordinates that are usually written horizontally. Coordinates that in your experience up to now have been written horizontally. It can be very convenient to write them vertically. We'll see a couple of reasons for this as we go through the course. One today that's marginally persuasive, but much better reasons will come up in Chapter 3. So anyway, it's another thing. All this means, a column V1, V2, V3. That just means V1, comma V2, comma V3. That's fine. Okay. All right. So now, do keep in mind, vectors have direction and length, but do not have location. Points have location, but do not have direction or length. So they're sort of complementary in the characteristics that they actually hold. And with that in mind, let's think now about this picture. What would I say about this vector in relation to that line? Now, there's a clear something's going on. I mean, this vector's got a glaring, strong relationship. I'm beating deliberately around the bush here with that line, and so there's a huge temptation. Students want to say, "Oh, that vector V. Look at this vector V. Here, I've got it right there. There it is. There's V. That purple vector V. That is in the line." Lots of students want to say this. That doesn't make any sense. You can't say that vector's in the line. Here's why. If you say the vector is in the line, in refers to a location. Vectors don't have a location. Right? They don't. So, in fact, if you were to say V is in the line, the appropriate interpretation would be, well, he said V. Okay, there's V. He said in. He's talking about the location of V. Oh, he must mean that we're thinking of V as being a point. What's the associated point to this vector V that we've drawn here? And of course, there's lots of other arrows here that represent this same vector, one of which is in standard position. And so the associated point is that right there. If you were going to give a location to V, that's the location of V, interpreted as a point. Now, is that point, I ask, rhetorically, is that point in the line L? Well, no. Not even close. Anybody on board? Okay. So you got to be careful with your terminology. V is not in the line. Now, okay, yeah, but still, come on, look, we've got this thing, right? I mean, I'm willing to grant that V is not in the line. By the way, here's another way to see that V. It'd be really poor choice of terminology to say V is in the line, because that vector, V, that's just as well represented by this arrow. Is this in the line? No, not in any sense, right? So, okay, so yeah, but what is the thing, though? I mean, I've still got this line, and there's still clearly something going on here. What is these clearly have something in common. What is this shared feature between that vector and that line? And that is that they're parallel. Right? The direction, vectors have direction. The direction associated with that vector, any one of these arrows, take your pick, I don't care. The direction is parallel to the direction of the line. So parallel makes sense. Now be careful with your terminology there. It's really easy to mess up and say V is in the line, and gotta watch out for mistakes like that. Okay. All right, so let's talk about a little bit of algebra of vectors. Given a vector here, V, what would be a good way to represent the magnitude of that? Well, here's a reasonable choice. We're going to represent vectors with arrows in such a way that the magnitude we're trying to represent is the length of the arrow. So when I ask, what's the magnitude of the vector? Another way to say that is, what's the length of the arrow? Another way to say length of the arrow is, well, I'm looking for the hypotenuse of this triangle. And we have a formula for that. This is the old Pythagorean theorem. I hope you all remember that one. Right. So here's a formula then for the magnitude of a vector. Okay. All right, now, what if we are in 3 dimensions? And here the problem gets a little bit more geometrically challenging. So let's suppose I have a vector like that. That vector has coordinates. If I wanted to draw the analogous picture, right, it'd be something like this. And what's the relationship between this length and those kind of 3? It's not a triangle. It's I don't know what that is. Right? But whatever that thing is, what's the relationship between those lengths? It's just a little bit of a geometry problem. I'm going to let you all work out the details. This is a nice exercise. Here's the big hint. The big hint is to draw the following line. And then notice that you have 2 triangles of interest. Let's see. There's this triangle, which is clearly a right triangle, by the way. Right? And then there's this triangle, which, by the way, also clearly a right triangle. And what I want to encourage y'all to do is to label this diagram appropriately, write down the Pythagorean relationship as it relates to each of these triangles, and then figure out how they combine together. It's just a matter of looking at the algebra, and you're basically going to take one and stick it inside of the other one. But when you do that, what you will conclude is this formula for the magnitude of a vector in R3 is that. So vector in R3, here's the formula for magnitude. Okay, nice exercise. Fill in the blanks on that. By the way, I do this a lot. I leave exercises to the class for things that we do in class. Again, we just don't have time to do everything in class. And plus, it is actually a really healthy educational part of the learning process to actually work some things out for yourself. Right. So that's there's multiple reasons why I'm leaving certain things for y'all to crank out on your own. That said, if you get stuck, come to office hours. We'll talk about it. We'll figure it out. Right. The help room, likewise. Don't forget the help room's open 2 to 6 every day. Well, 2 to 6 Monday through Friday, and that's a great place to get help as well. Okay. All right. Let's see here. So what does it mean to add 2 vectors? And there's different ways to approach this question of how to add vectors. One way is to say, well, I've got these coordinates over here. This is my first vector, and I've got these coordinates over here. That's my second vector, and I don't know. I guess I'll just add pairwise. I'll add the first coordinates or something, and I'll add the second coordinates. It seems kind of plausible or something. Okay, this is very bad, right? We're pulling something out of thin air. This is not a good motivation for a formula, for a definition. A new operation. What should it mean to add 2 vectors? We just made up these objects vectors. We don't want to just start making up random operations. Okay, so the way I like to approach this is to think about what it is that vectors represent. Vectors, among many other things, represent displacements, discrete movements. Right? So let's translate the question. What should it mean to add 2 displacements? And I think there's a pretty reasonable answer to that question. If you have a displacement, namely an instruction that says, hey, walk that way by that distance, that's a notion. Right, the concept of displacement of that sort. And then here's another notion of a displacement. Walk that direction by that distance. Each of these is an instruction. Right? What would it mean to add 2 such instructions? And I think this is a modest, reasonable proposition that, let's consider what happens then when I take a starting point and just successively first, follow the one instruction, do that first displacement, and then secondly, having done that, from that, temporary stopping point, let's from there, follow the other instruction. Do the other displacement. Altogether, then, the process of doing that first and that second has me having started there and ended there, namely altogether, you might say in total, I've displaced by that purple vector. Yeah? So I think this is a pretty reasonable candidate of something that we should call the sum of those two displacements. And displacements, of course, are represented by vectors. So the sum of two vectors, I nominate that this should be the picture on which we base our whatever formula we end up writing down. This is it's an important mathematical idea. When you write down a definition, don't just write down something that numerically or symbolically looks good on the page. Right? Think about how the operation that you're writing down or the object that you're writing down for whatever reason, what sort of natural process, natural object, what natural thing does that represent? And then let the naturality dictate what your definition should be. Right? So, said differently, definition should be based on ideas. It should not be based on notation. Okay. All right. So, with that in mind, and now here's another exercise for y'all to do on your own. But if you were to think of this, let's see, what notation did I use here? Yeah. If I were to think of this vector v as having coordinates of v1 and v2, if I were to think of this vector w as having coordinates w1 and w2, what would be the coordinates of v plus w? Look at this picture. Draw, what do we know about these coordinates that are given, and how does that relate to the picture? And what can I do with those to conclude v plus w's coordinates? And the answer is this right here, and it's exactly what we would have gotten had we taken the naive approach of, let's just add the first coordinates or something, right? Let's add the second coordinates. So that's a weird coincidence. I guess it's kind of good in a way. Sort of good news. It's also kind of, it's kind of bad in a way. It's, we had a much more sophisticated idea, yeah, we get the same answer. Anyway, so I think that's kind of amusing. Here, by the way, is one of the other reasons why I like writing vectors vertically. Here's my first example of why I like writing vectors vertically. Because I could rewrite this formula here, and let me zoom in for convenience. I could rewrite this formula as V1, V2 plus W1, W2 equals V1 plus W1, V2 plus W2, and notice that you can see just kind of row-wise, right, that we're adding corresponding coordinates. I'm adding the first coordinates and I'm adding the second coordinates. It looks good on the page. If you choose to, arbitrarily write the vectors vertically. There's that. Okay, how are we doing? Is everybody on board? Okay, moving along. What does it mean to multiply two vectors? Again, we could make something up. We could just, come up with some formula that's based on, symbolic laziness, right? And it's another situation where we would have gotten the right answer. But let's not do that. Let's think about this from a reasonable point of view. What should it mean if I have some displacement, and if I were to ask, what would be the interpretation of c times, real scalar, real value c times that displacement? I propose that a reasonable interpretation would be, just kind of keep going, just go c times as far. Right? So that would seem to be a good motivation for a definition, and not hard to come up with this as your resulting formula. And again, like I sort of hinted, this might be what you would have guessed should be the definition of scalar times vector had you had no geometric motivation. And if you're just looking at the symbols, this seems like a kind of a notationally reasonable thing to do as well. And again, good news, bad news, that's your choice. All right. Okay. All right. Now, does this make sense if C is negative? Is that reasonable? What you'll find is that this formula, if C is negative, will take a vector V, and following this formula will result in a vector like this. And I point out, this is actually pretty satisfying. This is kind of, I feel like, what we should have gotten. If C is negative, what's the interpretation of a negative, a minus sign on a displacement? Well, the minus sign kind of should be an opposite. And here this says we're going to go in the opposite direction. So, how about that? Works out just fine. Okay. All right. All right. Here's the next exercise for y'all to do on your own. I want y'all to prove this formula. Right here. And note carefully this absolute value of C here. That is a little bit of a surprise to some students. It is kind of feels like if you multiply a vector times a scalar, shouldn't you just multiply the magnitude of times that scalar? Isn't that what we said in the first place? Well, yeah, but honestly, when we drew this picture, when we drew this picture, we were kind of implicitly in the picture assuming C was positive, right? And then we have this kind of different picture if C is negative, and so there's something to discuss here. So I want you all to prove this one on your own. You have everything that you need to prove this formula. We have a formula for magnitudes, right? Just do this in 3 dimensions, by the way. It's fine. And we have a formula for what it means to multiply a vector times a scalar. So just break this down into coordinates, crank it out, and what you'll find is that this is exactly what you get. That this absolute value comes out automatically from the algebra. I will give you an algebraic heads up. This is to address what is a common misconception amongst high school algebra students. And, depending on what may or may not have come up in your calculus courses, you may not have seen the correction on this. A sizable fraction of Math 212 students do not know the following, and that is exactly what this symbol means. A lot of students mistakenly think that this is, different things. Some people think this means whichever square root of the two that you want. Right? Some students mistakenly think that symbol means both of the square roots. That's also wrong. That symbol does not mean both square roots. If you want to refer to both, you got to put a whole plus minus situation in the front and interpret appropriately. This symbol by itself, this means the positive square root. Not negative. So you got to be careful with that. It follows then that, for example, students are very comfortable having, I'll bet you a lot of y'all have seen the following a bunch of times. The square root of a squared is equal to a. That's not true as a general statement. Square root of a squared is not always equal to a. The square root of a squared is, however, always equal to the absolute value of a. Right? Think about, just let a equals -3 and think it through. Right? If a is -3, we're looking at the square root of 9, and the positive square root of 9 is not -3. It's +3. Everybody good? Okay, so keep this in mind as you go through and are doing this algebra. Okay, all right. Okay, so we've talked about addition. We've talked about scalar multiplication. How about subtraction? What should it mean to subtract 2 vectors? And before we, kind of go shopping on ideas, decide what we would like for subtraction to mean, let me point out that we don't actually have a choice. We've already bought, in some sense, as follows. That look, this subtraction, man, it really better be the same as this, and we've already decided what it means to multiply a scalar times a vector. We're stuck on that. right? And we have already decided what it means to add two vectors. So we're stuck on that. So unless we just don't want this algebra to be valid anymore, horror of thoughts, right? Can you imagine? We kind of have to make the definition of vector subtraction to be whatever this says. Right? So we don't get to choose anymore. Here is an equivalent, but I think more satisfying way to think about this. I like to think of this formula here, and that is the difference of two vectors, v minus w. Well, it's whatever you would have to add to w to get v. How about that? Right? And that does make for a very satisfying picture. Here it is. This is the way I like to think about vector subtraction. The difference of two vectors goes from the head of the one vector, the subtracted vector, in standard position, to the head of the first vector in standard position. And you can see right here that this is the thing that you add to that to get that. Okay. Okay, now here's a bunch of convenient rules of algebra. I'm going to very quickly point out that even though upon seeing these formulas, you might think, come on, yawn, right? And I saw these so long ago. In fact, didn't we see these in like elementary school or something? It's certainly middle school, right? Aren't these just the same statements? And technically, no. These are brand new statements. You've never seen these before at this point. And what I have to point out here is that this symbol, familiar though it looks, is brand new. We just defined that today, right? Because that symbol, even though it's the same symbol that we use to represent elementary school addition of real numbers, that's not what it's doing here. This symbol here is representing a brand new operation, the addition of vectors. Just defined it, right? And just because we had the audacity to use this symbol that that has established properties, right, doesn't mean that the new meaning that we're attributing to it also has those properties. So this is a brand new statement here that deserves to be proved. And I'm going to suggest that out of these 5 statements, pick one or two of them and prove them. These are easy proofs to do. All you have to do is say, look, we have a definition of v plus w. Just take let v be like v1, v2, v3. W be w1, w2, w3. You write down the definition of v plus w. And then write down the definition of w plus v. And then look at the coordinates and note that the coordinates are exactly the same. They're easy proofs, right? But nevertheless, that these do have to get done. So think those through. Everybody on board? Questions? By the way, just for class procedures, I have a tendency to kind of go on and on, right? This is not because I don't want questions, right? I do. Right, so do feel free to ask questions, and if I am at a moment where I'm going on and on a lot, just feel free to raise your hand. That's totally fine. I'll be happy to answer. Okay. Yeah.
So when we're proving these things, would you recommend, going through, separating each vector and actually writing out the coordinates?
Yeah, you want to write out the for example, on this one, write out the coordinates of c times v plus w. And those, by the way, here's a neat fact. All the coordinates will be, if you think about it, they're all real numbers, right? And so the formulas you'll have for those coordinates are formulas that involve what actually are our good old elementary school friends, plus and times, right? And then likewise, the coordinates of this will likewise be real numbers involving our old friends, plus and times. And so when you try to relate those coordinates, those slightly different formulas for those two slightly different vectors, those coordinates individually, you're just looking at elementary school or middle school algebra, whatever you want to call it. And then that is just super easy to say, come on, they're clearly the same formula because v1 plus w1 is already established to be the same as W1 plus V1. Yeah, totally. Okay, quick new idea. We're going to talk about something called a unit vector. A unit vector is just a vector whose magnitude is 1. That's all it is. It turns out unit vectors are useful and interesting in ways that will reveal themselves as we go through the course. Couple of quickie examples. Here's a couple of unit vectors. Not hard to see that those magnitudes are 1. Right. These are also interesting. These are what we call standard basis vectors in R2. These are the vectors that point along the axes. So these are going to come up a lot. I use the notation E1 and E2. Some people call these I and J. So you could call that, I hat, and this one J hat or J vector, whatever. I don't like this notation myself. The reason is that even though it's fine, if you're really sticking to just R2, that's fine, right? But in R3, what are you going to do? Well, in R3, you're going to have these vectors, and I guess you could call these, I, J, and K. Okay, fine, but what if you're doing economics and you've got 7 variables? And you're doing math in R7. Again, don't try to visualize it. The geometry is ridiculous, right? But you're still doing math in R7. You've got 7 different coordinates for any given point that you're dealing with. And what are you going to call those standard basis vectors? You're going to call them I, J, K, L, M, N, and O? I mean, it gets silly at some point, right? What if you have 28? Right? This notation here is very natural. You never run out of subscripts. Right? So, anyway. Okay. Last quick comment. Here's a handy-dandy formula. It comes up quite often. That we are given a vector, and we need to find the unit vector that points in the exact same direction as that given vector. This comes up a lot. And this is the handy-dandy formula for doing it. You take your original vector and divide it by its own magnitude. It's an easy argument to see why that works. If you take a vector and divide it by its own magnitude, that thing has magnitude which you can compute to be 1. And the computation is a very straightforward computation. There's a scalar. It factors out with the absolute value. This is clearly non-negative. So I don't need the absolute values, as it turns out. And then you notice, of course, that these just cancel, and you're left with 1. So it's an easy calculation. The point to this is not that it's hard to prove. The point to this is that it's really useful. And again, that'll play out over time. Okay, moving along to the next section. We're going to talk about how to multiply vectors. Okay, now this is tricky. Multiplying vectors. And so keep in mind the strategy that we want to take when we define operations is let's come up with a picture that seems like a natural, this is what it ought to mean to do the following operation. And once we know what it ought to look like, then it's just a matter of looking at the picture and interpreting appropriately and writing down the formula from that. Right? We let the interpretation dictate the formula. In an ideal world, what's going to happen here is that's actually pretty hard. I'm going to do this kind of backwards. I am just going to write down a formula, but I'm not just going to write down a formula and say, "So saith the math overlords." Right? I'm going to write down the formula, and then I owe you satisfaction that this is, in fact, geometrically natural in some ways. Right? So I'm going to, as a presentation though, it's going to seem a little bit backwards. By the way, before I get into that, here's another weird little quick thing. It turns out that there are two natural multiplications on vectors. It's weird. We're kind of accustomed to there being, this is what plus means and this is what times means. And, well, as it turns out, that does not imply that there's just one such operation. Just because we want it to be natural doesn't mean that there aren't kind of different ways to make natural things. Right? So we're going to find two pretty geometrically natural, pretty algebraically kind of like products constructions. So we're going to do them one at a time. This first one is called the dot product. And here it is. I'm going to define this for vectors in R3. If you have a couple of vectors in R3, here's our definition of the dot product of those two vectors. Weird little formula. Seems like something someone would just make up. Seems a little too arbitrary, simplistic, right? We're just going to multiply corresponding coordinates and then add them. It's also sort of just as an argument of type. It seems wrong. We're taking a product of two vectors, and the result is not a vector, right? Doesn't that seem kind of wrong? What we get is a scalar, not a vector. This is weird looking, unsatisfying looking. It turns out this is crazy natural in some impressive ways. First, I'm going to note some algebraic properties that this formula satisfies. Again, these are easily demonstrated. These you should be a little bit more interested in verifying, because these look. This dot product formula is highly suspicious, right? The addition formula we wrote down, it was really natural, right? But here, this is highly suspicious looking. Definitely want to check this, right? Or check all three of these. Just a matter of writing down both sides of the equation, no big deal. Confirm that it works. Should you be impressed with this? I'm going to say not really. These are just algebraic conveniences, right? You could argue that these are reasons why maybe we're going to find it convenient to have this as a definition. But does that make it natural? Is this geometrically natural? What does this have to do with the physical world? Am I going to use this, or do I just have a really convenient form of nonsense? Right? Got to worry about that. Okay. Here's the next observation I'll make. This formula, again, same dot product formula. The dot product of any vector with itself is its magnitude squared. And that's a little geometric. Right, we've got a dot product, and over on the right-hand side, we have a notion of length. That is intrinsically geometric. That is natural. So that's something, right? Now, don't be too impressed. This does not say all dot products are natural. Notice that this is just a dot product of a vector with itself. This makes no comment that a dot product of a vector with a different vector is in any way natural. So anyway, this is it's a first little appetizer of naturality. Okay, here's the next one. This is called the Cauchy-Schwarz inequality. By the way, whoever's going to take Math 216, we're going to spend a bunch of time talking about the Cauchy-Schwarz inequality. Actually, what you might call generalizations of the Cauchy-Schwarz inequality in different contexts, applied to different. We're going to generalize the idea of a dot product to a more abstract construction called an inner product, and there is a Cauchy-Schwarz inequality. So this will make sense in this other context as well. But anyway, here back in Math 212, here's a true statement about dot products. This is any dot product. Any dot product, they all have the feature that the absolute value is less than or equal to the product of the magnitudes of the individual vectors. How about that? Now, again, I claim that's pretty natural. This is any dot product. And over here on the right, I have length and length, and those are both geometrically natural, physically natural things. So this is a pretty clear connection to a natural, something that's natural. Now, confession, okay, it's not equals, it's just less than or equals. So, you could quibble persuasively and say, yeah, okay, so this is, in a halfway meaningless sense, connected to something natural, right? You could say the dot product is smaller than something natural. Or it doesn't mean that it is natural. Nevertheless, a little bit of an eyebrow raiser. Okay. Here's the one that I think is going to win you over. So why the dot product is natural, and this is this is true for any two non-zero vectors. The dot product, no asterisks, okay, non-zero. Okay, fine. Pretty much any dot product, and it's equal to a product of a magnitude and a cosine of an angle. And lengths and angles, again, very geometrically natural, physically natural. And this is equals. Right? So here we very literally have dot products are natural. I think that's very persuasive. Okay. The first time I saw this formula, I thought, come on, you got to be kidding me. How could this possibly be? Let's look back at the formula for dot product. Formula for dot product. It's just three-function arithmetic. We're multiplying and adding, perhaps the occasional subtraction if one of the coordinates is negative. A three-function arithmetic. And you're telling me that three-function arithmetic is equal to an expression that involves square roots, right? Magnitudes of square roots, and trigonometry. Right? Come on. This seems implausible on its face. But this is a true statement. And so this is, that observation, I think, should also be persuasive as to, why this construction, this seemingly strange, just multiply the corresponding coordinates and add. Why is that a natural thing? Well, oh my gosh, look at what it does for you. Okay. All right, so let me prove this formula. We're going to draw this picture where I've got the two vectors. I'm going to draw the angle theta, by the way, naturally as you would expect, as the angle between those two vectors. So this is a mathematical bank shot, I like to call them. We're going to prove the formula that we were just interested in by computing something that is neither of those things. So normally when you prove something, you start with this and you compute and then you confirm that you get that. Or you start with this and you compute and you confirm that you get that. I'm going to do neither of those things. I'm going to start by computing that thing. The magnitude squared of this difference vector v minus w for seemingly no apparent reason. So we want to get over to here, and we're going to get there by going that way. Right? So that's why, again, I call it a mathematical bank shot. It's a reference to pool, if you don't play pool or whatever. Okay. So here's how we prove this. Notice that we have here a triangle. Triangles are going to obey the law of cosines. Hope everybody remembers the law of cosines. Let me rephrase that. I know you have all forgotten the law of cosines. I hope you all remember that there was, way back in high school geometry, something called the law of cosines. And that you might even remember that it vaguely looked approximately something kind of sort of like this. But going forward, I do think it's an important thing to know. I think everyone should know the law of cosines. It's not a hard formula to remember. By the way, sidetrack, but notice that the law of cosines kind of looks like the Pythagorean formula. Got a triangle, and there's the Pythagorean seeming formula. It's just that this is not a right angle, and we have here what you might call a correction term for how to sort of fix the Pythagorean formula as it applies to non-right triangles. So anyway, something to think about. Okay, so that thing we're not interested in, there it is. Right, so this that vector magnitude squared is this. All right. Well, wait a second though. This thing that I'm not interested in, I also know that magnitude squared are a dot product of the vector with itself, so I can rewrite this as v minus w dot v minus w. And then I can take that dot product and I can FOIL that out like so. And in so foiling, notice that I get v dot v, well that's magnitude of v squared. And I get w dot w, that's magnitude of w squared. And so altogether I get that this thing, that I, again, don't really care about, just by kind of multiplying it all out, is equal to this. Okay, so I've got this thing that I don't care about, and I've computed it two different ways. I therefore have two things that I arguably kind of still don't really care about. But everything's about to come together. This and this are both equal to the same thing. Therefore, these two things are equal to each other. Those cancel. Those cancel. This factor of minus 2 in the remaining terms cancels. And as we were aiming for, v dot w is that thing that's left over. That's kind of cool how that algebra works out. Everybody happy? Okay, so nice. Okay, so this formula, our result here, this is a really important formula to know about dot products. So make sure to memorize that formula for sure. We're going to use it a lot. And now let me show you some sort of related things that you can do with it. One is you can use that to compute angles. If you're interested in the angle between two vectors, well, just solve for theta in that equation we just proved. And here you go. This is the angle between two given non-zero vectors. Just arc cosine. Okay. All right. Quick example. Suppose you got these two vectors here. Now these are a couple of vectors, and here's what's bad about those vectors. These are not in R2. There's a temptation to say, look, if you're in two dimensions, I don't need fancy dot product construct. If you're in two dimensions, just each one of the vectors, you can just compute the angle to a given axis and compute the angle of this one to that axis and just add and subtract appropriately, and you can find the angle between two vectors. But here we're in space, right? And so these two vectors are like, I don't know, maybe something like this. Right? When I say find the angle between them, I can't just sort of, I'll compute this angle, and then I'll compute that angle, and then having done those angles, I will then compute this angle, and no, because that's not the angle we're looking for. We're looking for the tilted angle between these two vectors. It's really, really not clear, without dot products, how would I compute that angle? And but with dot products, formula, right? You do have to compute the dot product and then the magnitudes to plug into that formula, but that's just a little bit of arithmetic, and the angle is, there you go. Everybody happy? Okay. Quick aside. Please don't plug this into a calculator. Calculators cannot compute this value. calculators can come up with an approximation to this value. And if we were, on our way out to the shop where we were going to cut a board, and I need to know what that length is because I need to know how to measure, I need to know exactly where to cut, then I need a decimal at that point. I'm not going to have any of that. There is no Math 212 shop. We're not cutting anything, and we want to leave answers as exact answers. This is a exact answer, aka a correct answer. And if you plug it into a calculator and give me a decimal, then your result is a little bit wrong. Everybody on board? Right. There's one exception to this rule. There's the occasional homework question where the algebra gets too unwieldy, and it's sort of necessary to, we're going to have to convert these into numbers so that we can actually add them up and crank them out. So there are a few such examples, but most of the time, if your answer ends up as something like this, there's no need to put it into a calculator and give me a decimal, and so just don't. Yeah. Okay. Corollary. Two non-zero vectors are perpendicular if and only if their dot product is 0. This is an easy argument to make. Let's look at our formula here. If I have a non-zero vector v and w, all right, so if this magnitude here is positive and if this magnitude here is positive, not 0, then if this is a right angle, then that makes this equal to 0, which makes this equal to 0. Right? Likewise, turning it around the other way, if this dot product is equal to 0, well, the dot product is equal to 0, that means that this product is equal to 0, but the first two factors can't be 0 because they're non-zero vectors, and that means that this has to equal to 0, and that means that this has to be pi over 2. Right? So the argument goes either way, and again we have this result. Perpendicular if and only if the dot product is 0. And that's nice. Okay, now there's a little asterisk. We keep in mind this only applies if the vectors are non-zero. So now let me say this theorem the way I really kind of should say it to be, thorough. If the dot product is, I'll say it this way. The dot product is 0 if and only if, well, there's several possibilities. It could be the vectors are perpendicular, or it could be that one of the vectors is 0, or it could be that the other vector is 0, or it could be that they're both 0. What a clunky thing to have to say, right? So in order to avoid that, sometimes, by the way, it just turns out that the dot product being 0 is actually more interesting than perpendicularity. And so we have a definition, a new term. A new term is orthogonal. And without wanting to quantify this, most of the time orthogonal means perpendicular. But to be precise, orthogonal means the dot product is 0. So from a geometric standpoint, orthogonal means that this long list of possibilities, well, either the vectors are perpendicular, or one of the vectors is the 0 vector, or the other vector is the 0 vector, or they're both the 0 vector. But it's a lot easier to think of it just as an algebraic thing. Okay. All right. So do be careful about the slight differences between these two terms, orthogonal and perpendicular. Orthogonal is a convenience. Orthogonality is your friend. If you have two vectors and if you know the dot product is 0, well, you're done. You know they're orthogonal. And the question of whether they're perpendicular or not, it boils down to a question of, well, is one of those vectors the 0 vector? Well, if one of the vectors is the 0 vector, it doesn't have a direction. And so perpendicularity loses all meaning, right? And so the word orthogonal just helps you from getting bogged down in those annoyances. Okay. All right. Easy example. I'm going to let y'all read that one. Okay, so let's talk about components. A couple of applications of dot products. Suppose I have a vector. Suppose also that I have a direction, a different direction that's indicated by this other vector, W. So I've got a vector V and this other vector W. I think it's an easy sale that there is exactly one way that I can write V as a sum of something parallel to W plus something perpendicular to W. Right? So take your vector V, write it in that way as, to what extent is it, what is the part that's parallel to W, what is the part that's perpendicular to W. The component is that magnitude. That's the component, what we call the W component. So we make a subscript of W there. The W component of V is that distance. Okay. So how do we compute that component? Turns out dot product, coincidentally you might say, just happens to be the perfect tool for doing this. And it's hard to see this coming. But let's, first thing I want to write down is looking at this picture. I want to write down, here let me zoom out so I can, here we go. So this component that I'm interested in is related to the magnitude of V by way of this angle, theta. Specifically the cosine of that angle theta. Right now it's just a matter of remembering your old trig. Hope everybody remembers trig. Trig's going to come up a lot in this class, by the way. So if you're a little shaky on your trig, you definitely want to polish off those skills. That's going to come up a lot. The cosine of that angle relates these two lengths, or said differently, the purple length is the green length times cosine theta. And having written that down, let's write it down a little bit differently. Here it is again. The formula that I just wrote down, component is that product. And then notice what I've done here is I've multiplied and divided by magnitude of W. That's just 1. Right? I just multiplied by 1. That's perfectly legal. And having done so, conveniently, that now is exactly the dot product. And here's my handy dandy formula for computing components. If you want to compute the component of one vector in the direction of another vector, there you go. Dot product is this fantastic tool. Yeah.
So in 3D space, what is theta, I guess?
So theta is the angle between the two vectors, right? So we've got this vector V that I'm actually interested in. That's the vector whose component I'm trying to compute. And then I've got this vector W that's defining the direction in which I want to compute its component. And so theta is the angle between those two vectors. Yeah. So the reason dot products come up is that you look at this formula and you can see right away that, well, if I want to compute that component, I'm going to need to know some trig involving that angle theta. And what does dot product do? Dot product involves trig involving that angle theta, right? It just happens to be that dot product and the component that we're interested in both involve the same trig, which is a lucky break. Okay. All right, so there you go. There is a nice special case that I'll point out, and this is just a special case. And let me zoom back in here. If it were to be hypothetically that the vector that's defining the direction, if that were a unit vector, that's a unit vector, then notice what I have over here. Here I have the magnitude of a unit vector, which is just 1. And so I don't even have to deal with that. It's just 1. And so at that point, my formula for the component is just a dot product. That's a really nice special case. Now, so again, this only works if the direction vector is a unit vector. It's got to be a unit vector for that to be true. But if so, components are dot products, and that's a nice it's a nice tool. It comes up a lot. It's going to come up a lot in this course. Okay. Last application we're going to talk about is work. Some of y'all may have had a physics course in the past. If you have, okay, cool. If you haven't, no sweat. We're going to do a little physics in this course, but it's not a great amount. What you need to know about work in this course is maybe a little context. So work is just a way of talking about how much energy it takes to perform a task. Right, so if I want to, here's this stylus. It doesn't weigh much, but it does take me a certain amount of energy, right, to lift that up. I just burned up some very teeny tiny fraction of a calorie in lifting that stylus up to a higher height. Right, so the way we keep track of that is work. And the formula for work that gets presented in high school physics classes is this. Work is equal to force times distance. Pretty plausible. Force, how heavy is the thing? Well, the heavier it is, the more work you're expending to lift it. The farther you lift it, the more work you're doing. If I were to lift this 10,000 feet, well, that's a lot more work than if I just lift it 2 feet. All right, so work is force times distance. This is how it gets written in high school. The problem is that force is actually a vector, right? And this is not recognizing that. Forces are vectors. This is treating force like it's a scalar. Now, that's not cool. Right? Likewise, displacements are vectors. Right? If I lift something up, well, it was here, it now is here, it has changed position as indicated by a vector, not a scalar. So this, likewise, is kind of not really representing the whole story. And you may be aware that there is an asterisk on this equation here. This asterisk is that, well, it's force times distance, but with the understanding that we're looking not at the actual force, but at the component of the force that's in the direction that you're actually moving. And so for example, if I were to put this stylus over here and then say, okay, let's displace by 2 feet, and you do your little work calculation. But if I move it this way, right, the force that I'm exerting is up, but the displacement is that way, and so I'm moving that way, but the force is that way. I'm actually not doing any work at all if I just do this. Right? In fact, I may be burning some calories because I'm being extremely inefficient here in holding it out. This is a silly way to move something horizontally. If you want to move something horizontally, put it on wheels, grease them up, give it a slight push, and just watch it go. It takes no energy at all. Right? So this asterisk is a consequence of the fact that we're ignoring the vector aspects of force and distance. And, well, details I'm going to let you all read on your own, but these are these are vectors. The force needs to actually be the appropriate component. Components are computed with dot products. And the nice punchline is, work is very simply the dot product of force interpreted as a vector and displacement interpreted as a vector. And this dot product keeps track of all of those directions and such for you. Right? The fact that we need the component of one in the direction of the other, and the magnitude and the this and the that, it all perfectly kept track of by the dot product. So I hope those of you who have had a physics class in the past, I hope you'll replace your old, in your mind, this old formula of work equals force times distance. I'd like you to throw that away, right? That is an oversimplified, let me rephrase that. This is an unnecessarily complicated way to think about work. That work is equal to force times distance, asterisk, with the understanding that you got to look at the component of one in the direction of the other and the cosine of the this and that. That's complicated. Here's the simple way to think about work. It's force dot displacement. End of story. Okay. All right. This makes a great stopping point. We are done with this section. This section 1.3, and we're going to pick up here with cross products and determinants on tomorrow. See y'all later.